So I'm pulling this example from the textbook and then modifying it a little bit, and I think it's a pretty good one for this topic. So let's let P be the population of a certain animal species, and this is going to be an egg-laying species, and we're actually going to also have a variable tracking the number of eggs that are around. And let's assume we're talking about large numbers, like huge population, huge number of eggs. Maybe you can imagine that we're measuring population in thousands of individuals and eggs in thousands of eggs or something, so that it makes sense to think of these as varying continuously rather than discretely. So let's assume that the population has a certain mortality rate, which is m per capita. So we're going to write down a differential equation system, basically, with these two being our unknown functions of time. So P and E are our dynamical variables. And we've got P prime is, so to start with, we've got this mortality rate, m. So when I say m per capita, that means, m is sort of the proportion that of the population that die in a given unit of time, except it's like an instantaneous version of that. Okay, so this is just like their natural dying rate. And if this were not an egg-laying species, then maybe I would just add like another parameter like alpha p like this and say alpha is their birth rate. And then it would actually just be one of these plain old unconstrained population growth differential equations. If their birth rate is bigger than their death rate, the population explodes. If their birth rate is smaller than their death rate, then the population dies off, and that would be very simple. But I'm not doing that, so there's no birth rate here. Instead, they become born through eggs. And there's like this separate egg-laying rate. So let's pretend, okay, so let me introduce that mechanic in a moment. But let's just look at the number of eggs that's laid by the population. So let's say that in any given unit of time, each member of the population lays B eggs. Then B times how many there are in the population is how many eggs you would expect to gain per unit time. So that is a positive contribution to E prime, the rate of change of the number of eggs over time. Okay, now this is how eggs get created, but there's one thing we have not paid attention to, which is how eggs get destroyed and how members of the population get created. And that's the same mechanism that will achieve that, which is an egg hatching. When an egg hatches, a new member of the population is introduced, and also that egg is destroyed, so it's no longer part of the count of the number of eggs. So let's say that egg hatching rate is h, little h, where it's kind of a proportion of the number of eggs. So per unit time, a proportion h of the eggs that are around will hatch. So it's sort of like almost like a radioactive process, like you have a bunch of eggs, and during any given time interval, there's a certain probability that any given egg is just going to hatch. I don't really know how egg hatching works, but it sounds like a decent model to me, I guess. Okay, so this egg hatching, this creates members of the population, but it also destroys eggs, right? And it's the same way h here and here. All right, so the eggs are getting destroyed at the same rate. So we can write this as, this vector P E equals, and then this matrix of coefficients P E. Prime here. Sorry, let me just put a big prime here. So how about I call it x? So let's just say x vector is going to be P e, these two functions of time, so that I can then write x prime equals that matrix x. So there's our differential equation. And right now it's homogeneous. Forgot the minus sign. So right now it's totally homogeneous. So you should actually know how to handle this kind of differential equation. If I tell you to write down the general solution, probably it would be very annoying and kind of challenging to do, because these are just parameters rather than numbers. I haven't fixed these parameters as numbers. I'm leaving them kind of free to vary. So it would be pretty involved to write the general solution. But we can, remember, we have ways of learning a lot about these systems without writing the general solution down. So we can look at the determinant and the trace. And we can also look at, we can start trying to get the eigenvalues of this matrix and just go far enough to see what conditions will cause the eigenvalues to be complex versus real. That's actually not too hard to do. One interesting one to look at here is the determinant. So let's examine that. The determinant is negative m negative h, so mh, minus bh. Okay, so m minus b h. And question, is that positive or negative? Well, it depends on whether m is bigger than b or b is bigger than m, right? So now we're seeing an interesting pair of cases here. If m is bigger than b, something will happen. If m is less than b, something will happen. So if you want, actually I'd suggest you pause the video now and just, without writing anything down, just think through what do you think are the differences in the behaviors. And okay, now I'm assuming you've thought through whatever you wanted to think through of that, and here's what I'm going to do with it. So if m is bigger than b, then the determinant is positive. If m is less than b, the determinant is negative, right? And here's one where we can immediately say something. If the determinant is negative, then we have a saddle point, right? That means the eigenvalues are real, and you have one positive and one negative, right? Remember, the determinant is the product of the eigenvalues. That can only be negative if they're real and opposite signs. So immediately we know that one eigenvalue is positive, one negative. One lambda is positive, other is negative. And we also know the picture, right? The picture is something like this for the solutions. But it would be nice to get a more accurate picture than that, but it's going to be some kind of saddle point. I guess it'd be nice to know which way the eigendirections actually point. On the other hand, if m is greater than b, then you're looking at this, well then I guess you need to look at the trace, right? So the trace is negative m plus negative h, right? Negative m plus h. Now, I forgot to say it up here, but m, h, and b are all positive numbers. We're trying to interpret m as a mortality rate here, and b as a sort of birth rate, but it's more of an egg hatching rate. Sorry, not egg hatching rate, egg laying rate. So that's b. So we want these to be positive. So definitely, and h is supposed to be an egg hatching rate. That's supposed to be positive. So the trace is negative, right? The trace is always negative. Down here, in this case, we don't care that the trace is negative, because knowing that the determinant is negative was enough information for us. But over here, it matters, because that tells us that, well, we don't know, in the positive determinant case, we don't know whether we have a stable node or we don't know whether we have real or complex eigenvalues, but this tells us that if the eigenvalues are real, then we're looking at a stable node rather than an unstable node. And if the eigenvalues are complex, then we're looking at a stable spiral rather than an unstable spiral. So immediately we know we're looking at a stable node or a stable spiral. And that means node or spiral. So that means everything goes towards the origin, right? So in PE space, population versus egg count space, stable node means things are just coming to the origin, right? And stable spiral also means things are coming to the origin. They're just spiraling in. That's terrible, right? That means everyone dies. That's the conclusion, is that everyone dies in this population. Does that make sense? Yeah, if the mortality rate is too high, yes, everyone dies, right? If the mortality rate is higher than the egg-laying rate, then eventually everyone dies. If the mortality rate is less than the egg-laying rate, then you get some different behavior. And to be clear here, let me just draw this again. PE. Here's our spiral. I don't know if I'm orienting it the right way, but actually let me make sure I do orient it the right way for this picture. Let me just do this old trick that I was doing before. If x is 1, 0, so if the population is, if I have no eggs and some amount of population, then I'll get negative mb, which points to the left and up. So if I have some population but no eggs, then we point to the left and up like that. That sounds like we're spiraling in like that. Okay, so let me just draw it from here. How about? Like that, right? But what's happening here is the like your population maybe starts out here and there's no eggs. They lay eggs, but they also gradually die, right? And eventually you reach here. Now everyone's dead, but there's still eggs. At this point, the population can't go negative, so the differential equation stops applying. Really, we should just delete this part, right? So once you reach here, there's a totally different differential equation that you should be using. I guess when this is the state of your system, you have everyone dead, but there's still eggs lying around which can hatch. But I think from here I would expect, you know, the hatching rate that you get due to the amount of eggs that you have would just lead this way, and we could analyze that. So eventually everyone dies, but it's more like this. It is a spiral, but you wouldn't see an actual spiral since you can't have negative population. Okay, so that's kind of interesting. I guess I'd like to have a nicer picture for the, you know, I don't know why I erased that. I guess I'd like to have a nicer picture for the saddle point case. But I really don't want to go through and get the eigenvectors by hand with the parameters here. All right, so I just did this. And I wonder if I can, so these are the two eigenvectors. And I haven't put in any assumptions here, so like as far as Mathematica knows here, the thing under the square root could be negative, and we could be in the complex eigenvalues case, but I'm imagining the situation where m is less than b here. And apparently, since that leads to negative determinant, you cannot have complex eigenvalues, so that should guarantee that this thing under the square root is positive. So I guess judging by the minus sign here and the plus sign there, this must be the eigenvalue that's associated with the, this must be the negative of it. When you're in this case, determinant less than 0, one of the eigenvalues is negative, the other is positive, right? This must be the negative one, since this is definitely less than this one. This must be the positive one. So this is one eigenvalue, another eigenvalue. Here's the eigenvector that goes with the first eigenvalue. So this eigenvector goes with the negative eigenvalue. This one goes with the positive. And I'm really just doing this to see if I can draw a picture of these. So let me think about this. Maybe I'll do some of this off screen since it's actually not too important for the example. I just would like to have a nice picture. Okay, I just realized when I was thinking about this that the direction that these eigenvectors point in depends on the sign of m minus h. So it depends on whether the mortality rate is bigger than or less than the egg hatching rate, which I'm trying to draw a picture that applies to the situation where m is less than b. So I don't know whether m is less than or greater than h. So I guess I have to make two pictures here, one for m less than h and one for m greater than h. Okay, after thinking about it for a while, I realized I was wrong. It doesn't matter whether m is less than h or bigger than h. Regardless, you get one of your eigenvectors being in this quadrant and the other one being in that quadrant. Or, one of your straight lines along an eigenvector being like this, and the other one being like this. One positively sloped, one negatively sloped. And I also found that the one corresponding to the positive eigenvalue is this one, and the one corresponding to the negative eigenvalue is this one. We actually only care about stuff going on in this region because you can only have positive population and positive number of eggs. And yeah, so you get solutions like this, right? The positive eigenvalue, you have these, the negative like this, but nothing's happening over here for us. So we just have these kinds of things. And in fact, we should really cut off our entire picture here. Okay, so basically your egg population, your number of eggs and your population just shoots off along this line here and just approaches this line. But both are growing, population and eggs. It's a population explosion. Okay, so if your mortality rate is higher than your egg-laying rate, then everyone dies. If mortality rate is lower than the egg-laying rate, then there's a population explosion. Stable node or stable spiral, depending on other things, and here, saddle point. Okay, so that was all homogeneous, right? This is a homogeneous linear system. The point of this was to actually show you how do we now then deal with the non-homogeneous situation. So this example was really fun to think about just this. Before I add in, I'm going to add like a predator eating the eggs. But this was just fun to think about, so I kind of got sidetracked with it. But how about in the next video, we'll actually put in the non-homogeneous part and think about that.